In this three-part series, we are building an AI real estate voice agent that can interact with the user, collect their preferences, recommend tailored properties, and schedule a showing, all without no human interaction. Let's kick this off with a quick demo so you can see exactly how powerful this AI real estate agent is.
Thank you for calling Joy and Grace Realty. How may I help you today?
Hi, I'm looking for a single family.
May I know your name?
My name is Jerry.
Great to meet you, Jerry. What's a good phone number to reach you at so I can follow up?
Sure, it's 3.
Thank you, Jerry. Just to confirm, is that
Yeah, that is correct. Yes.
perfect? Are you looking to buy or rent?
I'm looking to buy.
Okay, great. And where are you hoping to find this property?
In Chicago.
Thanks. How much space are you looking for in square feet?
3,000 square feet.
Got it. Do you have a budget in mind for this purchase?
Around 300,000.
Perfect. How many bedrooms are you hoping for and how many bathrooms?
3 beds and 2 bathrooms.
Thank you, Jerry. This is great. Now, what are some features that the property absolutely must have? And what are some things that would be nice to have but aren't essential?
Sure. I have 2 young kids, so definitely grade schools is a must, and a big backyard would be a bonus.
All right, Jerry, I think I have a really good understanding of what you're looking for. Just one last quick review. You're looking to buy a single-family home in Chicago, around 3,000 square feet, with 3 bedrooms and 2 bathrooms. You absolutely need access to a grade school and would love a big backyard. Does that sound right?
Yeah, that sounds correct. Yes.
I found a couple of exciting properties for you, Jerry. First, there's a beautiful single-family home located in the heart of Bridgeport. It's listed at $265,212 and has 4 spacious bedrooms and 2 well-appointed bathrooms with over 3,161 square feet. It features a chef's kitchen with granite countertops, a cozy private patio, and it's close to top-rated schools. It blends comfort, style, and convenience. A fantastic option. Would you like to schedule a showing for this property?
Yeah, sounds great. How about Tuesday at 9 a.m.?
It looks like the earliest available time on Tuesday is 9 a.m. Would you like to go with that time?
Yeah, let's do it. Yep.
Your appointment has been scheduled for Tuesday at 9 a.m. to view the beautiful single-family home in Bridgeport. If you have any questions or need further assistance before then, feel free to reach out. Happy house hunting, Jerry.
Now, this isn't just a fancy appointment scheduler. That would be too easy. No. Our assistant carefully handpicks property listings tailored to exactly what the user wants. It's not pulling random listings from a database. Instead, it is using semantic search to deliver personalized recommendations. And what's even better, we will continually maintain a real-time feeding of listings directly from the realtor, making sure recommendations stay fresh and relevant. If you missed part 1, you definitely want to pause here and watch that first, because we unpacked a ton of important concepts. We walked through the full architecture of this AI agent. I explained my tech stack and the tools I chose, why I picked Python over n8n for agent's core logic, why PydanticAI over CrewAI, why ChromaDB made sense, and why WAPI was the ideal choice for voice integration. I shared my thought process, design decisions, key considerations, and even gave you behind-the-scenes look at exactly how I approach building this from scratch. If you haven't seen it, trust me, pause this video, go watch part 1 and then come back here. If you want a voice assistant like this for your business or something completely custom, we can help. Whether it's handling inbound calls, following up with leads, or automating something totally unique, we will help you figure it out. Book a free consultation call with us. The link is right on the screen and also in the description below. Back to building this awesome assistant. In this video, we are diving even deeper. We'll unpack exactly how the agent is designed. We'll talk specifically about Pydantic AI, why I chose it, and how I implemented agents and how everything ties together. We'll dig into prompt engineering. I'll show you exactly how I crafted effective prompts for this voice agent. We'll discuss LLM selection, specifically why I went with GPT-4o Mini. We'll explore the property recommendation logic in detail, why correctly storing property listing matters using RAG and semantic search. I'll give you practical semantic search examples, how we loaded properties into ChromaDB and prepared them properly, a detailed walkthrough of all the source code, and we'll wrap it up with a demo. Before we jump into the code and setup, let's quickly recap the high-level architecture one more time. Here's what happens when a caller calls in. VAPI handles the incoming phone call. It listens and converts speech to text and passes the conversation to our Python-based AI agent built using Pydantic AI. Our agent does the heavy lifting. It understands what the buyer wants, collects preferences smoothly, and instantly queries a vector search database. We use ChromaDB to find the perfect property matches. Once it finds ideal properties, it uses n8n, a simple but powerful automation tool, to seamlessly book an appointment directly into the agent's Google Calendar. Finally, Twilio sends an immediate SMS or WhatsApp message with the appointment details back to the buyer. This entire flow is streamlined, automated, and completely hands-off. If you haven't watched the part 1 of the series, I strongly recommend you to watch. I covered reasons for why we chose these tools that you see in the architecture for this specific use case. All right, let's get practical and see how do you actually set this project up yourself. The entire source code for this project is in Git, under AI in Real World, and under the repo named Real Estate Agent. First, issue a git clone command to clone the project locally in your system. Next up, open the project in VS Code. All the dependent libraries required for this project is defined in requirements.txt file. To install the dependencies, you have two easy options. Option 1. In VS Code, press Ctrl-Shift-P, then select the Python interpreter. VS Code will suggest you create a new virtual environment and go ahead and do it. It will also see the requirements.txt file in the project and ask if you want to use the requirements.txt file to install the dependencies. Go ahead and say yes. And this is option 1. Option 2 is the manual method. First, you create a virtual environment using python-m command, and then you activate the virtual environment. Finally, you install dependencies manually by running pip install -r requirements.txt. Just a quick note. During installation, if you hit an error stating you need Microsoft Visual C++ 14.0 or greater to install ChromaDB, just install the Visual C++ build tools from the official link. I'll include the link in the description. Next, you need to set the environment variables. Rename the .env.example file to .env and fill in all the required API keys and secrets. Let's now go to VS Code and quickly tour how the project is structured. All our source code is under the SRC folder. The agent folder contains all the Pydantic AI agent definitions. Tools folder contains agent-specific tools for recommendations, appointment availability checks, and scheduling appointments. Data folder contains scripts and data for loading, vectorizing, and preparing property listings into ChromaDB. Models folder has Pydantic models for key entities like user profile, recommendations, and scheduling info. Utils folder has utilities for datetime parsing, scheduling logic, and vector embedding. At the root of source, you will find two handy scripts. Chat.py runs our agent in a simple text chat mode for easy debugging and testing. Voice_vapi.py runs the agent with Vapi integration for voice-based interactions. Don't worry, we'll walk through all these scripts in detail shortly. Also, outside the SRC folder, you will see .env.example file. Remember to copy this file and rename it to .env file and provide the API keys for all the missing entries. Requirements.txt has all the dependencies neatly listed. The n8n folder contains n8n workflow for Google Calendar and Twilio integrations. And finally, a comprehensive README file in the project root with extra helpful information. Let's get into the heart of the design, our Pydantic AI agent. Pydantic AI essentially has two core components, agent and tools. Agent are your primary interface to interact with LLMs. When you define an agent, you specify the LLM to use, like GPT-4o Mini or Claude Sonnet, etc. The system prompt clearly defining agents' roles and goals, and dependencies like embeddings, databases, external services that are available at runtime for the agent to use. The beautiful thing is defining an agent in Pydantic AI does not require tons of boilerplate code. It is simple and elegant. Tools are what your agent uses at runtime to perform specific tasks. Tools can be custom Python functions you write to handle database calls, external APIs, or other complex logic. At runtime, the LLM automatically determines which tool to invoke based on context, making interactions feel seamless and natural. Here's how it works. When a user calls our agent, WAPI converts the speech to text and passes the text to the Pydantic agent. Agent then determines the intent of the caller, calls the appropriate tool, such as recommend underscore properties for recommending properties, or scheduling underscore appointment for scheduling an appointment. Tools perform the actual logic and the structured results are sent back to the agent. Agent conversationally communicates the results back to the user. It genuinely feels like magic when you see it working, but we'll unpack exactly how this magic happens when we dive deep into the code. Initially, I thought I would probably need two separate agents. My reasoning was, well, one agent could be responsible purely for collecting user preferences, like budget, bedrooms, neighborhoods, and all that good stuff. And then I would have another dedicated agent just to handle scheduling and calendar integrations. Seems neat, right? Separation of concerns and all that. As I started coding and testing, and remember, I always test quickly in text mode first, I realized something interesting. Keeping it as one agent was actually way simpler. I ended up pushing everything into just one conversational agent. And guess what? It worked perfectly. But here's why it worked so smoothly, and this is key. I did not cram the agent full of complex logic for calendars or scheduling. Instead, I offloaded all the tricky bits, checking availabilities, booking appointments, to separate tools. These tools basically take structure input from the agent, handle all the messy details like parsing dates, checking calendar availability, and returning clear, structured responses back to the agent. This meant my main agent had a crystal clear job: collect user preferences naturally and conversationally, then choose and call the correct tool at the exact right moment to make property recommendations, get realtors availability, and schedule an appointment. Honestly, once the prompting was clear and structured, the agent easily figured out which tool to use every single time. No confusion, no mistakes. So instead of two separate agents, I ended up with one streamlined agent calling specialized tools. And the best part, the clarity in prompting made this setup practically bulletproof. So there you have it. That's exactly how the agent evolved from an initial two-agent idea into a simpler, cleaner, single-agent setup with clear tools. Let's jump into the detailed code walkthrough now. Open up realtor underscore agent in the agent directory. This file right here is our AI agent. From here, you will see this crucial line of code. Here we have defined a Pydantic AI agent. This single agent handles the entire conversation from collecting buyer preferences to recommending properties and scheduling appointments. It responds conversationally, clearly, and quickly to buyers, making the interactions natural. It decides exactly when to call specific tools based on structured responses and clear prompting. All logic related to appointments and recommendations is cleanly handled in external tools, keeping the agent lightweight and focused. Let's break this down carefully, because understanding this part is key to understand how the entire thing works. Model parameter specifies exactly which LLM, large language model, we are using. And for this project, we are using OpenAI's GPT-4o Mini. I'll explain shortly why I chose this model specifically. Prompt equals system prompt defines the exact instructions that guide our agent. Basically, it provides the agent with role, tone, goals, and guidelines. The temperature parameter controls the randomness of the generated text. Adjusting the temperature changes how the model selects the next word in a sequence, influencing the creativity and predictability of the output. Lower temperature renders outputs that are predictable and repetitive. Higher temperatures favors creativity. Lower temperature less than 1 encourages predictability and it is ideal for our application. The output underscore type parameter defines the type of the output from our agent. In our case, it is plain old string. Instrument equals true indicate that we need to log the agent interaction with tools, LLM, etc. Easy for troubleshooting. The dependencies underscore type parameter, which is assigned to agent dependencies object. Let's talk about that. Both agent dependencies and system prompt are defined in agent underscore config under the agents folder. Let's take a look at agent dependencies first. Notice the data class decorator at the top. If you're new to Python data classes, they're basically a convenient way to automatically generate special methods like init for your classes. It helps us keep things clean and organized without boilerplate. Here is exactly what each property does. Chroma underscore client, this is the persistent client we use to interact with the ChromaDB database. It handles semantic searches and property recommendations. ChromaDB listings, a simple string reference to the specific ChromaDB collection, storing our property listing. N8N webhook URL. The webhook URL we use to communicate with our N8N workflows, which is used for Google Calendar and Twilio integration. Finally, we got agent schedule config, an object holding a realtor's working schedule preferences, like working hours, appointment durations, buffer times, and time zone. And here's a quick look at agent schedule config. Let's talk about something super important, prompt engineering. Look, I've seen countless YouTube shorts and Instagram reels claiming stuff like, use this exact magic prompt, and AI will magically do exactly what you want. Honestly, prompting does not work like that in real life. Prompt engineering, in my experience, goes something like this. You experiment, you fail, you tweak, and you try again. There is no universal step-by-step recipe I can give you that will perfectly cover every scenario you will face. Now, I can definitely share guidelines, best practices, and examples. But the truth is, you just gotta put in the reps. The more you write prompts, the faster you will get. Eventually, you won't feel like you're starting from zero every time. Also keep in mind, prompts heavily depend on the LLM you're using. A prompt that gives you perfect results with OpenAI's GPT-4o might behave completely different when you try it with an Anthropic model. You just have to be ready to adapt and iterate constantly. Let's jump into the actual prompt now. It is defined in agentconfig.py. Inside this file, you'll see exactly how detailed and structured my prompt is. Let me quickly walk you through each section, explaining why I structured it this way and what I learned along the way. My prompt has several key sections to define the role, tone, goal, rules, and guidelines to the agent. Right at the start, the prompt clearly explained the agent's role, tone, and goal. You are a friendly and enthusiastic virtual real estate assistant. You speak in a warm, polite tone, but you're also concise and to the point. This clearly defines the agent's role and tone. Next, we say prospective buyers or renters call you for help. Your job is to quickly collect the preferences, recommend properties that match, schedule a showing if they're interested. This defines the overall goal for the agent. Initially, my wording was different. I prompted, your goal is to fill in user preferences. And guess what happened? The agent would respond robotically. Something like, I've updated your name as Jerry, but I'm missing preferences like your phone number and email. It sounded awkward and unnatural. I quickly realized just changing fill in to collect user preferences prompted the AI to behave more naturally. Next, we give some details on what are some of the key pieces of information we want to collect from the caller. Information like budget, location, number of bedrooms, bathrooms, etc. We also provide some examples on how to follow up on missing preferences. Using these examples, LLM will adapt and ask questions. Once all user preferences are collected, we prompt the LLM to confirm the preferences to the caller. We also prompt on how to recommend properties. When I first started, property recommendations sounded stiff. Caller would hear all 3 property recommendations at once. Also, LLM returned recommendation 1, single family home, Lincoln Park, price $500,000. And the voice model will emit exactly that. This is okay for text chat, but not great for voice conversations. So I tweak the prompt to include friendly conversational examples like, okay, I found a charming home in a great neighborhood. It's located in 627 Logan Boulevard, listed at $375,000 with 3 bedrooms and 2 baths. The kitchen was renovated and there is a huge backyard perfect for summer barbecue. And instantly, Recommendations felt warm, conversational, and human-like. I also had to explicitly prompt to the agent to recommend one properties at a time so it does not list all three recommendations at once. This could be overwhelming for the caller. Also, prompted to ask if the caller would like to schedule a showing after each recommendation. This simple change drastically improved how natural the conversation felt. Finally, date and time handling. I had specific instructions for dates and times because, as I mentioned earlier, LLMs are frozen in time. They don't understand next Monday naturally. So we prompted the LLM not to convert phrases like tomorrow or next Monday. We had specific code in place in our tools to handle dates and time. More on this when we dive deeper into scheduling in part 3 of this video series. Now you might look at my detailed prompt and think, wow, how did he even come up with all these nice prompts? He must be really good at prompts. The honest answer, lots of trial and error. Check my Git commit history. You'll clearly see how my prompt evolved over time. It didn't start out perfect. I refined it continuously as I noticed awkward interactions or unclear responses. So seriously, don't feel overwhelmed if your first prompts aren't perfect. Keep iterating, tweaking, and learning. Also, use ChatGPT to refine your prompts. Give your current prompt to ChatGPT, explain what isn't working. ChatGPT will refine the prompt and even make suggestions to the overall prompt. Go back to realtor_agent Python script. Let's talk briefly about why I chose OpenAI's GPT-4o Mini for this project. Why OpenAI? Honestly, not because it's the only good option, but simply because I've built a few applications already using models from OpenAI, and notably GPT-4o. It's like having a personal doctor, someone who knows you, understands your needs, and someone you trust implicitly. Switching to a completely different model, even if technically great, felt unnecessary for this project. But why GPT-4o specifically? And why the mini version? GPT-4o is one of OpenAI's newest models, good enough to handle complex tasks like conversational agents. And why mini? Simple, speed and latency. Voice interactions absolutely demand responses under a second. GPT-4o Mini consistently delivers lightning-fast results. When scaling or deploying something bigger, I always evaluate 4 things. Effectiveness of the model for the use case in hand, meaning, does it respond in the way we like? The second would be cost, and the third would be context window, meaning how many tokens the model can handle at once. And finally, the response time. GPT-4o Mini fits the bill perfectly for now. If needs change, I'll adjust accordingly. And speaking of trying different LLMs, using OpenRouter is fantastic because it lets me experiment with tons of models like Anthropic or DeepSeek, all without managing separate integration or accounts. Using OpenRouter's API, switching providers or testing new models becomes super easy. It's a huge productivity booster. You can see I'm overriding the OpenRouter model with OpenAI and going straight to OpenAI. And this is because the response time with OpenAI was better than that of OpenRouter. You can also completely comment out the OpenRouter code that you see here. For voice agents, we want to keep the latency very low. And hence, I went ahead with OpenAI. So that's the detailed story of exactly how I configured the agent. Carefully crafted the prompt through lots of trial and error and thoughtfully picked GPT-4o Mini as my LLM. Let's get practical now. Let's talk about exactly how the agent collects user preferences, because this step is crucial. If the agent does not clearly understand what buyer wants, everything else falls apart. So open user profile Python script under models folder with me. This file right here defines exactly how we structure and validate user preferences. This user profile model uses Pydantic to neatly capture everything a buyer might mention, like budget, location, property type, and specific features. It ensures structured data, making it easy to validate and process. When the agent interacts with the user, it continuously fills in these fields naturally, conversationally guided by our carefully crafted system prompt. Once these fields are captured, our agent uses this structured info to recommend suitable properties. So the prompt we previously discussed in agent config Python script is super important here. It explicitly instructs the agent to naturally collect these user preferences during conversation. The prompt essentially guides the agent to gently fill out this user profile, asking clear questions and confirming key details in a conversational way. Along with user profile, we have few helper functions that helps us to validate and refine the properties in user profile. Validate user profile function does validation checks on user profile and make sure the object has all the needed information to make property recommendations. That is, whether it has a name, valid phone number, do we have budget, etc. If any of this key information is missing or not in the format we prefer, the function will return what is missing. The validate phone number function here makes sure we have a valid phone number. Apply defaults to profile function applies default values to any missing preferences. For example, if square feet information is missing, we default to 2000 square feet. And this could totally happen even if agent repeatedly asking for a specific user preference and the caller failed to provide information about the preference. Now let's talk about something critical, normalizing the user profile data. This is hugely important and here is why. Suppose a caller casually says my budget is 300K. We can store 300K as 300K. It needs to be consistent and searchable like 300,000. Another example is phone number. They must be in proper E164 international format. That is, it should start with plus country code. If a phone number is not stored in a very specific format, Twilio later in the integration will refuse to send SMS messages. So let's quickly see exactly how we handle these scenarios clearly and consistently. Here is our main normalize function. Normalize user profile. We call a series of normalization helpers to clearly format each individual attribute. Let's take normalize price as a quick example. It converts various budget formats like 300K or 1.5 million into neat integers like 300,000 or 1.5 million. Why go through all this trouble? When we query ChromaDB for property recommendations, we run a quick preliminary number filter first on preferences like budget, bedrooms, bathrooms to narrow down search results. Then we perform a semantic search only on the filtered listing. It dramatically speeds up searches and keep recommendations precise and relevant. Now, if you're new to an agent framework like Pydantic, you're probably thinking, wait, who exactly fills out the user profile object? How are these normalization functions triggered at runtime? How does our agent even know and how to call our custom tools like recommend properties? Let me clearly unpack this step by step. Who fills out the user profile object? It is filled out by the LLM, our GPT-4o Mini. The LLM uses a conversational interaction and carefully crafted prompts to populate the user profile object. Now, how does the agent know about the recommend properties too? Great question. To clearly expose a function as a tool to our agent, we simply decorate it with @realtor_agent.tool. Realtor_agent is a reference to our agent. This decorator clearly registers the function as an available tool at runtime. How does the agent know when and how to call this tool? Another great question. It all comes down to your prompt. The prompt clearly instructs the LLM when it should fetch property recommendations. At runtime, PydanticAI clearly exposes the registered tool recommend_properties to the LLM. The LLM reads our prompt and figures out the right moment to call the tool based on the ongoing conversation. The LLM knows the exact tool signature. It understands it needs a user profile object and fills it out automatically before invoking the tool. All of this complexity, knowing when to call the tool, populating the object is completely handled by PydanticAI and the LLM under the hood. It genuinely feels like magic. Since the agent has enough user preferences captured in the structured form, it automatically calls our tool recommend properties. This is why user profile is a Pydantic object, so we can control how LLM should pass the information to the tool. Let's now look at how property recommendations are made. Open up recommend_properties Python script. It is under agents tools folder. This tool takes the structured buyer preferences captured in our user profile model, validates the object using the function defined in user profile script, which we saw before. If the object is missing any key information, we return the validation errors back to the LLM. This will prompt the LLM to ask the caller for missing information. We then normalize the user profile object using the normalize user profile function. We now have a user profile object which has all the required properties filled out and with clean, properly formatted values. Now we have caller's preferences neatly captured. We are ready to recommend properties based on user preferences. To make this possible, we use a vector database where we store all the current property listings. First, a quick reality check. Large language models like our GPT-4o Mini don't actually have access to real-time information. So you can ask them, hey, what's on Zillow right now? They simply don't know. To solve this, we need an external way to quickly and effectively query structured property information. This is where a vector database like ChromaDB shines. But wait, what exactly is a vector database? And what are vector embeddings? And all these fancy terms. Here's the simplest way to understand it clearly. Vectors are just numeric representations of text or concepts. Think of vector as coordinates in an imaginary space. Embeddings are the numeric vectors we create from text data, capturing meaning and context. For example, modern condo in downtown Chicago becomes a unique numeric vector. A vector database stores all these numeric embeddings efficiently, allowing rapid semantic searches based on meaning, not just exact keyword matches. Storing text as numbers helps a vector database match text based on semantic meaning. Here's a quick semantic example. If you search modern downtown apartment, a traditional database might miss to match property listings described as contemporary condo near city center. Even though they're practically the same, a vector database catches these nuances instantly. That's a super quick introduction to vector database. In this project, we use ChromaDB and we run it locally. To recommend properties tool, this tool takes the structured buyer preferences captured in our user profile model and converts them into a vector embedding. It then queries ChromaDB vector database to quickly find the closest matching properties. Once it fetches relevant property listings, it formats them to structured recommendations. These recommendations then get returned to the agent, which naturally presents them back to the caller. To make this work, we first had to create some data. So I quickly generated a data set of 1,000 realistic property listings for Chicago using ChatGPT and stored it as JSON under the data folder in files Chicago listings 1000.json. You will replace this dataset with real property listings. You can either get the live data through listing provider like MLS, or you can set up an automated process to get the data from the realtor using a daily file import. The prompt to create this dataset is super simple. I simply prompted, give me 1,000 sample real estate listings for Chicago, downloadable in JSON format, complete with detailed, realistic descriptions, typically returned by realtors. Model the listings closely on the actual listings for realism. That is it. ChatGPT gave me 1,000 realistic looking property listings. We loaded this dataset into ChromaDB using load_listings Python script under the data folder. Here is exactly what the load listing Python script does. It reads the listing in the JSON file, reads 100 listings at a time, and insert the data into ChromaDB. We add 4 set of collections into Chroma. Documents. For each listings, we turn the listing into descriptive text by calling the function generatePropertyText. So a JSON listing like this will be converted to something like single family for sale with 3 beds and 2 baths in Logan Square priced at $500,000. Something like that. The text is then passed to getOpenEmbeddings function to get the embeddings. This is important. Each listing is turned into vector embeddings. To turn text to embeddings, we use OpenAI's text embedding 3 small model. We then neatly store these embeddings in ChromaDB, ready for fast queries. Semantic searches in the database are performed against these embeddings. In addition to storing the vector embeddings of property listings, we store the property listings assets and metadata and store the IDs of the property listings separately as well. The database name in ChromaDB is real_estate_listings. First thing, we have a handy little script, query_listings Python script under the data folder. This script lets me directly query ChromaDB manually. Super useful when testing recommendations during development. Let's see if ChromaDB is working properly. Let's query ChromaDB with this text. Townhome, 3 bedrooms, 2 bathrooms, 450,000 budget in Chicago, must have garage, backyards, good to haves, near train station, finished basement. This text will be first converted to vector embeddings using OpenAI's text embedding 3 small model. Then we use these embeddings to query ChromaDB. Let's run the script and see the results. And we got the results. This means our ChromaDB is working as expected. You might notice the properties returned does not perfectly match the preferences mentioned in the query text. We can improve that, and we'll see how shortly. With this, we can confirm that we can query ChromaDB and our ChromaDB is working properly. Now we have the property listings data in vector database ChromaDB. let's see how we can use the data to make recommendations matching user preferences. Back to recommend underscore properties tool. Once we have the user profile validated and normalized, we pass the user profile to profile to text function defined in embeddings util Python script under the utils folder. This utility function simply takes our structured user profile and converts it into text like 3-bedroom townhouse in West Loop, 400K, etc. Then uses our embedding model, OpenAI's embedding API, to convert that text into numeric vectors. Into numeric vectors, ChromaDB understands. We then send this embedding directly to ChromaDB as a query. ChromaDB returns the top matching properties instantly. First, get a reference to the data in ChromaDB by calling getCollection, passing in the database name, real estate listing. Next, we call the query function, passing in the embedding, which is the vector representation of user preferences along with a where condition, where we filter on all the hard preferences like budget, location, price, square feet, bedrooms, etc. We limit the results to 3. Once we have the results, we pass the results to parse Chroma results. This helper function simply cleans up and formats raw search results from ChromaDB into structured property recommendation model, which the agent can clearly and easily interpret. How the LLM should deal with these property recommendation is specified in the prompt. We want the LLM to offer one recommendation at a time, followed by asking the caller if he wants to schedule a showing. Also, each recommendation should be read out naturally and not like bulleted points. We have also provided an example style on how the recommendation should be made to the caller. Let's take a quick step back and recap what we have seen so far. Our agent is now able to collect user preferences like location, budget, number of bedrooms, etc., and then make tailored property recommendations using those preferences. The magic behind this is a RAG-style setup, retrieval augmented generation. We are using semantic search powered by ChromaDB to find the most relevant properties based on what the user says, not just keyword matches, but actual intent. All right. Now, how do we test all this? So here is something I do with almost every voice project. I always start with a simple text-based chatbot. Not because the final product is text, but because it's faster to iterate that way. You catch bugs quicker. You don't have to listen to audio over and over. It's just faster and more convenient to test logic flow and functionality in plain text. But I'm also very aware that what works in a text interface does not always translate to a good voice experience. Let me give you a specific example. If you're chatting with the bot, it gives you 3 property recommendations in a single message, each one clearly formatted with bullet points. It looks great, right? Super readable. But that same message read out loud over the phone can feel overwhelming. You got too many details at once and no visual anchors. That's the kind of nuance you only catch when testing with real voice. But for early iterations, text is the way to go. So to test what we have so far, I've written a Python script called chat.py, located under the src folder. It acts as a quick command line interface where I can simulate conversations with the agent, pass user preferences, and inspect the recommendation the agent returns. This helps validate everything from the prompt formatting to the property selection logic to whether ChromaDB is returning good matches. Let's now walk through the code step by step. Let's start with these 3 imports first. These are the modules we have written. Realtor agent is the actual AI agent that handles the conversation. Agent dependencies is a container where we group up things the agent will need, like database clients and other configuration. Agent schedule config define things like the working hours of the realtor, realtor's time zone, and few other things for the realtor. This comes into play during appointment scheduling. This configures logfire. We only send logs if a token is present in the environment. Next, we define the set of dependencies required for the agent and its tools to perform the job at runtime. These dependencies are passed to the agent on every call, so it knows where to find ChromaDB listings, where to send scheduling requests via Inaden, what is the working hours for the realtor, and other schedule configurations specific to the realtor when suggesting available time slots. We now instantiate the agent itself and its dependencies. We start with the default message to kick things off and an empty list to hold the message history. Model message is what PydanticAI uses to maintain conversational context over multiple turns. This is our main Ripple-style chat loop. This allows us to type exit or quit to break out of the loop. This is the core call. We pass the user's message, all dependencies the agent needs, the full message history so the agent can respond contextually. We pass in the message history so it includes both user message and the agent response. This ensures the future turns are grounded in prior context. We output the agent's reply, and finally, we wait for the next user message. This script is intentionally simple. The goal is to test how the agent behaves in different conversational flows without having to wait on voice and deal with WAPI calls or recompile anything. It's fast, lightweight, and gives you full visibility into what the agent is doing, which is exactly what you want when debugging behavior or refining prompts. We are now ready to test the major capability of our agent, collecting user preferences and making property recommendations. We'll do two tests. In the first test, we are going to go step by step. As the agent asks questions, we'll provide one preference at a time, just like a real user would on a call. In the second test, we'll give it multiple preferences all at once and see how it handles it. We're also going to try tweaking our preferences mid-conversation and watch how the agent adapts. Okay, let's run the script. Okay, first the agent is asking for my name. So I'm going to say Jerry. Next, the agent is asking for a good phone number. So I'm going to give a fake phone number. So I'm going to say 123. All right, let's do that. That's good enough. Okay, so here the agent is confirming the phone number. And because in our prompts, we have asked the agent to confirm the phone number. I'm going to say yes to this. Now the agent is asking if we are interested in buying or renting. I'm going to say buy. And where are we hoping to find this property? I'm going to say Chicago. So the next question is, are we looking for a house or an apartment? I'm going to say house. Now it's asking for the square feet. I'm going to say 3,000. Budget. I'm going to say under 300K. How many bedrooms? 3 bedrooms, 3 bed and 2 bath. Now it's asking for what are some of the must-have features and nice-to-have. So I'm going to say for must-have, I'm going to say great schools is a must-have, and nearby restaurants is good to have. All right, this is basically confirming all our preferences that we have entered so far. So I'm going to say yes. Now you can see how the preferences are clearly normalized, right? Especially for the budget, we said under 300K, right? So here you see a numeric value, which is 300,000. And you can also see the must-haves listed as great schools and good-to-haves as nearby restaurants. We said 3 bed and 2 bath, so it inferred correctly. So for bedrooms, it has 3. And for bathrooms, it has 2. And it also gave a recommendation, right? And the recommendation is nicely summarized. Beautiful single-family home located in Bridgeport, and it's listed at 265K, which is under 300K because that's our preference. And this recommendation is actually matching to our must-have and nice-to-have because it is saying that this property listing also is near top-rated schools and restaurants. Finally, it's asking, would you like to schedule a showing for this property? So the agent captures all this, all our preferences, runs a ChromaDB semantic search, and gives us a recommendation that matches what we have asked for. It only gave us one recommendation, and that's intentional. We don't want to overwhelm the user with too many options, especially once this becomes a voice conversations. Too many options can be overwhelming. The summary of the property we have here is great. Short, natural, and high impact. I really like how the LLM wrote the summary highlighting the features of the property listing, matching with the caller's preference. Finally, it offers to schedule a showing. We'll talk more about how we tackle scheduling, Google Calendar integration, and Twilio integration, along with voice integration with WAPI in the next video, which is part 3 and the final part of the series. But for now, let's move to our second test. In this one, we're going to push the agent a bit more. Instead of answering questions one by one, we'll give it all our preferences at once. like some real world callers might do. So let's say something like, I'm looking to buy a single family in Chicago with 3 bedrooms and 2 bathrooms, and my budget is $700K, all in one line. So that's 6 preferences in one go. By intent, property type, location, number of bedrooms, number of bathrooms, and budget. And finally, when the agent offers recommendations, we'll ask for other recommendations. And we can also change our preferences to see what the agent does. All right, I'm going to X out of this program first. Open a new terminal. Start the program again. Okay, it's asking for my name. I'm going to type in Jerry. All right, asking for my phone number. Again, I'll make up something. All right, cool. Yes, that's my phone number. Okay, so here I'm going to say, I'm looking to buy a single family in Chicago with 3 bedrooms, 2 bathrooms, and my budget is $700K. That's a lot of user preferences in one go. So the agent rightly inferred that I have not provided a square footage. So it's asking for that. I'm going to say 3,000. Again, it's asking for must have and nice to have. I'm going to say restaurants must have, and a big backyard would be nice to have. It's now giving me a recap. So let's see. We're looking to buy a single family in Chicago, 3 bedrooms, 2 bath, with a budget of $700,000 with a square footage of 3,000. It has got everything correct, right? We gave a lot of user preferences at once, and it inferred everything correctly so far. I'm going to say yes. It looks like the recommendation is also spot on. And we got one recommendation. It is well within our budget of $681,000, and our budget is $700,000. So I'm going to say, give me another recommendation. Or actually better, I'll say like, give me another property. Okay, this time again, we got another property. The listing price is less than our budget, $662,000. Okay, now we'll change things up a bit. Now I'm going to say my budget is now 1 million, and we'll ask the agent to make recommendations. Actually, you know what? My budget is 1 million. Show me what you got. Now look at our input to the recommend properties too, right? Especially focus on the budget. Our budget is now 1 million. It's not 700,000 anymore. You can see now the new recommendation is under our new budget. Our new budget is 1 million, and this property is listed at 991,000. This is exactly the kind of dynamic, adaptive behavior we want from a smart assistant. And everything is working just like we expected. And that's a great place to wrap this video. In the next video, which is part 3 and the final part of the series, we're going to tackle appointment scheduling. We'll walk through how we use Google Calendar to check availability of the realtor, and how we use Twilio to send confirmations by SMS or WhatsApp to the caller. We'll automate the whole flow using an agent, and most importantly, integrate real voice conversations using Vapi. If you want a voice assistant like this for your business or something completely custom, we can help. Whether it's handling inbound calls, following up with leads, or automating something totally unique, we will help you figure out every step of the way. Book a free consultation call with us. Link is right here on the screen and also in the description below. Next video is going to be packed, and honestly, it's where the whole project starts to feel magical. So if you're not subscribed already, definitely hit that subscribe button so you don't miss it. See you in the next one.